Okay. All right, so we're going to go ahead and start plowing through the book, unless someone has any other questions about this course before I begin.
Kind of dinosaurs have.
Extinct.
Yeah, I was thinking black and red, maybe a little tan. I don't know why they went with dinosaurs, but they did. All right. So chapter 1 is going to cover a ton of different topics. Unfortunately, chapter 1 it's more of a, you need to just memorize all these terms kind of more than anything else, because we need to lay the groundwork to start learning about where we're going next in this course. So this is we just got to go through a lot of material. You may not be able to pick all of it up. That's okay, I understand. We're going to be revisiting most of this throughout the course, but we need to at least have a good high-level view of what's happening. All right. That's what I just said. Oh, yes. And next, this is really the next iteration after computer architecture. Architecture really dealt with how to design and create a processor. Now, what software runs first on that processor, which is really the operating system? How is a piece of software running on our hardware going to present a clean interface to user applications? All right, the author usually calls it a program that acts as an intermediary between a user, computer, and computer hardware. That kind of follows the picture we came up earlier. It really is just all the software between your user program and your hardware. But it is important to realize that the operating system is really the first thing that's called after the hardware accomplishes some task. So yeah, it's usually divided in main components, or your computer is. You got hardware, OS, application, your users. All right, hardware, computer architecture, OS, what we're doing here. Applications, you've probably all written applications like in data structures and Java, and you've done internships, that's what you've done most of. And then your user, most of the time it's your people, but do keep in mind that a user can be another machine. Especially when you start talking about client-server interaction, a machine may be another user or computer. All right, this is a decent hierarchy. Hardware, operating systems on top of the hardware, applications on top of the OS, and then the user is interfacing into the operating system, or into the applications that are running on top of the operating system. Any questions on this? Got the nice, that's going to be the standard stack, standard flow. So the operating system is a resource allocator. It detects what resources you have, what hardware, how much memory, if you have network cards, what monitors you have, and then it allocates it to the applications as the applications request the different hardware. It also has to control it to try and prevent any errors or improper use of the computer. What does that sound like to you? Improper use. I guess maybe another question is the improper use intentional or unintentional?
Security.
Both. Yeah, trick question, sorry. Yeah, it's both. You'll have people who just accidentally do certain things, but you will have people intentionally trying to break into your system. And so you need to be prepared to defend against that. As he says, there's no universally accepted definition, but I think the picture earlier really helps define it. The reason why it's kind of hard to define it is if you think about that whole stack, obviously the operating system is the first software that runs on top of the hardware, but the software that's between the application and the OS blurs a lot. A lot of times people think of it as maybe just a shared library, which may not be considered the OS. Other people will say, well, since it's a library that's shared, the OS is managing it, which makes it part of the OS. All I'm trying to say is it can get a little blurry up top with your applications, but definitely concrete for sure. Your operating system is the first piece of software on top of your hardware. And that piece of software that's right on top of the hardware is called your kernel. And kernel is always part of the operating system, not the whole thing. Yeah, that's a good way of putting it. The OS is always running, but you never clicked it to start it. All right, Bootstrap program is a little different. When your computer turns on, it can't just start the operating system. It needs to figure out, well, there's a bootstrap program that basically loads the kernel into memory, sets up the kernel so it can start running, and then kicks it off. And this is actually the first thing that happens inside of any boot up sequence. Have any of y'all seen Grub or Lilo or anything like that? Grub? Yeah, if you've used Grub before, that's what they're talking about as a bootstrap program. Because with Grub, you can actually select which operating system you want. So it's trying to bootstrap or get things up running. Also, it can be used to load firmware as well. That is true. I got cut off. It is best to think about this, even though we're talking about the stack of hardware, software, application software, user. Really, your computer is a bunch of different components trying to communicate with one another. Because you have your CPU, it's talking to the memory, dealing with memory. It's talking to disk controllers, talking to USB controllers, graphics drivers. I mean, you can also have, what else is on this list actually? Let's go that way. Graphics driver, USB, disk, CPU, memory, network, that's a good one. Okay, USB controller is going to handle a lot of mouse, keyboard, and printer. Yeah, USB is pretty universal here, so it's going to cover up a whole lot of them. Yeah, so I guess we're not going to talk about different serial connections as well. But yeah, network's a good one that's missing. Could you have more than one CPU? Or more than one display driver? Yeah, so you could actually copy and paste a lot of these components as well. You have multiple disk controllers. You can actually have multiple memories if you want. Although that, hopefully after taking this course, you'll see why in general that is not a good idea. All right, the first bullet here is why a lot of things start to become really sad in operating systems. All your I/O and the CPU execute concurrently, meaning when you hit something on the keyboard, the computer is doing something completely different. So that means while you're trying to do one thing, something else is happening, and now you have to manage how are we going to merge those two things together to actually make something useful happen. And when it comes down to all I/O, which means pretty much anything, disk controller, USB, all the USB, your monitor, and to some extent your memory, you can consider it I/O as well. All these things are happening concurrently. We need to somehow serialize this or make it usable to the end user, because the CPU, at least when we're talking about single CPU systems, is only doing one thing at a time. And I think that covers this slide well. So the question is, how does this CPU actually handle all these different I/O operations happening at once? Well, there's something called an interrupt vector. What does that sound like to y'all? Or did we just say it right up here? Interrupt vector. So it's a vector, meaning it's a array. And all it is addresses of service routines. So it's literally the address of a function, aka a piece of code to call. So what it's saying is, if you're going to have this giant array, worker time. Ooh. All right, I'm going to try and not hit anyone. Oh, so close. One day I'll get it. Thank you, Tyler.
Is the entire wall a whiteboard now?
Yes, the entire wall is a whiteboard. Yeah. Pretty awesome, although it's kind of, that's fine. So you might have 0x, 3f, or 35, because that's what I wrote that time, 0x, fa, 0x, 3b. Obviously, these are going to be a lot longer than this, but the idea is that if interrupt 0 came in, you would know it needs to start executing code at memory address 35. If interrupt 2 came in, it would know it need to execute the service routine at memory address 3b. That's all it is. So you have this array, your interrupt vector, telling you what piece of code to execute when an interrupt occurs. So address of the interrupted instruction. What does this mean? So if the interrupt comes in right here, it knows it needs to execute this piece of code. What state is the CPU in? What if we'll say we're in a, well actually, what state is the CPU in? Anyone from architecture?
Resting?
Could be resting. Could it be executing another program?
Yeah.
Could be executing another program. What if it's doing a mathematical calculation right now?
Ideally, or for the most part, your CPU should be doing something.
Yeah, so it's doing some work. So if it's doing work over here, this is your register file, and then maybe you'll have your ALU might be processing, I don't know, multiplication right now. And all of a sudden you get an interrupt. Someone hit a key on the keyboard, and you want to handle this interrupt. What do you need to do with your CPU? Store what?
All current state.
Its current state. Why do you want to store its state?
Well, you want the numbers it was dealing with, so that right before that, you want the address of the instruction it was dealing with.
Right. You don't want to terminate the program that's running on here.
Right.
You want to be able to save this out, so after you handle the interrupt, you can come back to the CPU and still execute that program. We'll go more in detail of what exactly is going on, but keep in mind that it has to save everything. So your register file, your program counter, any of the interrupt flags that are on it, all the different, everything of the CPU has to be saved out. So really the first thing that happens, by the way, if you ever look at the code, it jumps to this memory address. The first thing that's called, save the CPU state to memory. Then it executes its instructions. So that's what an interrupt is. A trap, you're going to get these two confused. A trap is a software-generated interrupt caused by an error or user request. So it's saying like, okay, I want to wait for the keyboard to say something. You can trap your process telling the OS, hey, I'm done for now. Or hey, there's a software error, send a trap, the operating system, you need to kill the process, it's not working correctly anymore. The key is the trap is coming from your application, the interrupt is coming from your hardware. That's the difference. Any questions? All right, and I think I can do this. And I can go up. Oh, I almost got it up on. All right. Right, you got to preserve the state, determine which type of interrupt has occurred. Okay, there are polling interrupts, but in general, it's a type of vector interrupt. You've hit something on the keyboard. A polling one's usually coming from a timer. Hey, you know, a 60th of a second went by. Do you need to do something? There might be something you need to do every 60th of a second. And I talked about the vector, which tells you what piece of code to execute. Okay. Let me see if I can explain this graph. It's confusing at first. There's really two graphs going on here. You have your top line, which is what the user process and the I/O interrupting, aka the application, the operating system. So the application's running, the operating system's running, the application's running, the operating system's running, the application's running. Okay? That's what's happening on the CPU. On the I/O device, it's idle or transferring. So idle, it's not doing anything. Oh, it needs to transfer data, you know, some keyboard strokes. Now it's back to idle, meaning that it's completed all the data it needs to transfer. It's in some type of buffer. And then the operating system says, okay, let's go ahead and interrupt the CPU and start reading that data out and then give control back to the user. Then later on, hey, it happens again, transferring, oh, I'm ready. Interrupt goes through, do some processing, back to the user. That's all it's saying. But keep in mind that there is not only is there a delay in transferring the data, there's usually a delay between transferring the data being done and interrupting the CPU in order to execute, to work on that interrupt. That's, I think, one of the big things to get from this picture. All right. right, so after I/O starts, control returns to user program only after it's completed. So after you've written all the information from the CPU out to memory and you've done your interrupt handling, what do you need to do next?
Load it all back.
Yeah, load it all back into the CPU. You got it. And then hopefully return execution. Won't go into too much detail, but hopefully you can see that if you have an in-order pipeline or a superscalar out-of-order pipeline, that can be really complicated. All right. Talks a little bit more about that. Control returns, waiting for it. A lot of times an interrupt will come from a system call. You want to read from the hard drive. Well, that's, you're requesting something from an I/O device. So you'll return from a system call. That's usually how it's handled. Device status table contains the entry for each I/O device, telling you the type, address, and state. There is a table. Also in your CPU, you usually have flags or bits telling you about the status of certain interrupts. And those are usually part of your CPU architecture. We didn't design that in our processor because we want to keep it simple, but those bits are usually in there. And then you would index into that table to figure out its state. All right, any questions? I'm going over a lot, so if you need a break, please tell me. I feel like I'm just plowing through all these high-level ideas. All right, direct memory access. This is particularly for high speed. The idea is that your device controller transfers blocks of data from buffered storage directly out to memory. Okay, what's going on here is you have your giant piece of memory, maybe from 0x0 down to 0x f, 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 dot, 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 right? The idea is direct memory access. You're going to reserve maybe this piece right here will represent your video card. You want to write some data out to your video card, or maybe it'll represent something on your hard disk. Well, the idea is that if you write something here, it's really forwarding that directly to your hardware device, hence direct memory access. Also, if you read from it, same thing. So it's just mapping a certain memory space to represent your hardware. And this is usually okay because your memory space nowadays is 64 bits, and no one has that much RAM lying around. So you have plenty of space in order to address it for your hard drive, or for your device. The point here is only one interrupt is generated per block rather than one per each byte, so it can aid and stop having to do all these interrupts back and forth. Because really, hopefully as you can tell, writing out the CPU, reading it back in is a very costly operation. So you want to minimize that as much as possible. All right. Main memory, large storage that the CPU can access directly. Secondary is usually an extension of the main memory. Provides large non-volatile storage capacity. We're going to talk a lot more about virtual memory here. We touched base on it in architecture. Y'all probably did in applied systems, is that right? Or applied systems?
Yes.
Yeah, you did. Okay, great. So actually, the real question I need to ask is, did anyone take applied systems and not computer architecture last semester? Okay, kind of. But everyone, okay, good. All right, so we're all on the same track. All right, magnetic disks. We'll go in a lot more detail about how they work with tracks and sectors, why they're set up the way they are. But you do need a disk controller that resides on the hard drive itself to communicate to the operating systems. By the way, this disk controller on a rotating disk is incredibly complex. It'll get kernel level complex just to manage that hard drive. It is actually a lot of software running on an individual piece of, on an individual hard drive. All right, so you've all taken architecture. Was caching important? No, not at all. Not at all. All right. Well, the doors no. So, caching is incredibly important. In architecture, we talked about caching in the CPU with a level 1 or level 2 cache. That is going to extend into operating systems. You will have different ways to cache in main memory your I/O device or stuff that's coming from I/O. Because if your hard drive takes millions of cycles, but your memory only takes maybe 1,000 or actually 100, if you can buffer some of your hard drive information in your main memory, you're going to save a lot when it comes to speed, aka performance. Make sense? Nothing new there for everyone that's taking architecture? Yeah. Okay. So, speed, cost, and volatility. Caching is one thing to increase speed, although it usually has a cost associated with it. Here's an extended hierarchy of the memory. Registers on your CPU, cache usually on your CPU as well, but it's larger. Main memory larger than your cache. We'll usually talk about electronic disk, aka solid state drives, are usually a lot faster than your magnetic disks, but in general they store less information, although that's starting to blur, which is going to be awesome. Hopefully we'll have more and more solid state drives take over. Magnetic disks still will hold more. I think they just released one, was it 10 or 20 terabytes in one disk or something? I'd have to go look it up again. But they can hold, each disk can hold a lot on the magnetic side. Optical disks, again, can store a lot. They're usually read-only. And then tapes, yeah, believe it or not, we still have tapes. And they store, I forget what it was. It was almost 100 terabytes or something crazy that you can do on a tape drive. But tape drive, if you need access and it's on the other end of the tape, you gotta wait for it to rewind. That's just the way it is. Great for backups, right? Because you're just sequentially spitting everything out or writing everything to it, but that's about it. Any questions about this? The idea is that registers up top, small and fast, bottom, big and slow. Hopefully I've beaten you to death with caching. Making something smaller so it's faster, and try and keep everything inside the cache as much as possible. All right. Okay. Historically, I would say until, I don't know, late 90s. So actually, that's probably history now, early 2000s for a lot of y'all. But most machines were a single processor. You had one core doing the work. You just executed one instruction after another, and that was it. There was no extra multiprocessing going on. Multiprocessing systems have been around for a very long time. 60s, 70s, they've been around. No, multiprocessor is a little different than multi-core. Multi-core is you have multiple cores on one processor, while multiprocessor is you have two of them, or more than one. Parallel systems. The idea is you want to increase your throughput, and usually it's economy of scale, because since you're buying a separate system, you can just hook them up. AKA, you just buy one of these, one of those, you hook them up with a network cable. Hey, it's a multi-processing system as long as you can distribute jobs to each one of them. Why is reliability increased? This is important. If you have multi-processor, aka we'll just say more than one machine.
The other one stays up.
The other one can stay up, right? So one goes down, hopefully the other guy's basically a mirror, and then you can just jump over to that one. So if you had 5 of these and they were mirroring each other, 3 of them go down, you can still service. Although you probably will have not as much throughput as if you had all 5 running, but at least you can, they'll go to the web page. It may take a couple seconds now, but at least it'll come up. All right, you have asymmetric, multiprocessing, and symmetric. I think the slides are going to go to what those mean soon. Maybe? We'll talk about this first. So this is the standard model for computers. CPU, a thread of execution with cache, talking with the instruction data memory, and you usually have direct memory address. That's what I was talking about in order to talk to your device. AKA, if you address something here, it's actually going straight here. I/O, data, and interrupt. Hopefully this picture's straightforward. Any questions on this? I'm gonna let y'all look at it for a while, because I don't have too much to say besides the picture makes sense. Good so far? No questions? All right, great. Here we go, symmetric. Key piece of information, they're sharing memory. They have their own cache, their own registers, but each cache is a copy of main memory, which means that each cache might have multiple copies of someone else's cache inside of them. Okay? So symmetric, you're sharing your memory. Dual core, oh, here's the point. So symmetric multiprocessing, notice you have CPU, CPU, CPU. Multi-core, CPU, core 0, core 1. You just have, they're basically built inside the processor. High level, it kind of looks like what's the big deal? The big thing is in multi-core, since the cores are next to each other, most of the time they're not showing it here, but they have this, right? They'll have a direct line between the two caches so that they communicate very quickly. Over here, that's not going to happen because you have to jump outside the processor to get to the other person's cache. So the one advantage of multi-core here is that you can directly tie the two caches together. Asymmetric, by the way, is he has his memory, he has his memory, he has his memory. So they really are not sharing unless you explicitly make them share. All right. Let's see, clustered. Right, this one. Okay, cluster, you have a cluster of machines. Some clusters are for high performance computing. It's also good for high availability. Anyone familiar with that term, high availability? You want to make sure your system's available as much as possible, so you have clustered machines mirroring each other essentially. So if one goes down, your service is still available because you have at least one machine to service. You also use clusters for high performance. A lot of the supercomputers have thousands or millions of cores. You're not going to put 1,000 cores on one processor. I'm sure someone's done it, but it's just not practical, right? You got to have multiple machines running around. That's where high performance computing comes in as well. Naturally, the difficulty here is you have to write a very parallelizable application, which is not always feasible. And these slides should be posted on GitHub. If they're not, definitely email me. All right, multi-programming. So multi-programming organizes jobs, so CPU only has one to execute a subset. So the idea is you may have multiple jobs. All right, so we got to switch gears a little here, because multitasking is not necessarily multi-core. Multitasking means that your computer is giving you the illusion, at least, of running multiple tasks simultaneously. You can still do this off of one core by quickly switching between different tasks as you're operating. I mean, if your clock's at gigahertz, you can do a lot of things inside of 1 second. So you can flip between different tasks. And I mean, our eyes only see, 30 frames per second at most? Well, I guess some people are better, but even at that rate, you can still flip between different tasks and give the illusion that you're accomplishing something, or that they're running simultaneously, even though they're not. But that's the point. Multitasking is you're switching jobs so frequently, the users can interact with each job while it's running. It's creating this illusion that everything is running at the same time, which in multi-core it may actually be, or it may not. Fast response time, that's what you need. Each user may have one process. So first off, the OS has to make sure the response time is pretty good. Got to figure out how to manage that. We might have multiple programs running at once. Okay, we need to manage all these different programs. We call them a process. When the CPU is ready to execute and we have multiple jobs running around, well, which one do we schedule next? And how do we schedule it? How long does it run? When do we know to stop? As the deal with scheduling. That's going to be a big topic. If they don't fit in memory, we're out of memory, but we have virtual memory, which is something on the hard disk. We need to dump it to the hard drive, but how do we choose which one to dump to the hard drive? And then virtual memory, which basically back to swapping, moves them in and out to run. Virtual memory is where you dump them when you're swapping them, putting them to the virtual memory or the hard drive. Any questions? Nope. All right. So here's you might have your operating system code, your process code, maybe some of the process memory. This might be some OS memory that has to use job 2, job 3, job 4. How do we know which one to run? Because also, the thing to keep in mind is job 2 is waiting for something from I/O to complete, and it hasn't happened yet. You don't need to execute on the CPU. It's not going to do anything. So you can just skip it and go to job 3. But at the same time, if it's waiting for something from I/O, you probably want it to execute very quickly when the I/O completes. So you need to have some type of prioritization there. But that's just an example. This is how it's laid out in memory. All right, pulling it back to interrupts. Interrupts driven by hardware. That's where you get software gives you the traps, aka divide by 0. And then you have something called dual mode, where you have user mode and kernel mode. Are any of y'all familiar with these two modes? All right. So this is actually a good question. Kernel mode will have privileged rights, meaning that they can execute things in the kernel. They can directly tell a hardware device to do something. A user, when you're in user mode, you can't. You're not allowed to access certain pieces of hardware. Why would we split these two?
Keep you from accidentally messing something up.
So accidentally messing something up, that's good. But more today, why would the DoD be very interested in this would probably be a better way to put it.
Keep people from purposely messing.
Yeah, purposely messing with it. User wants access to some encrypted device. He doesn't have access in user mode. The CPU, since it's a hardware feature, they can't run any code to access that, period. The hardware will stop them. In kernel mode, they can. But in user mode, you still want to be able to get something from the keyboard. So how would the user be able to get something from the kernel? That can only be done in kernel mode. Let's see if it says it. It does. Oh, perfect. System call. You make a system call, and when you make a system call, you are basically setting up a request to the kernel saying, I'm requesting this from the hard drive, or I'm requesting this. Sends a trap. It's a trap because it's coming from software. It's not an interrupt. An interrupt would come from hardware. A trap comes from software. First thing the kernel does, save the state of your program off. Maybe it can handle it, maybe it can't. If it can't, your program's going to wait a while until it finally completes. When it completes, it's going to return from the system call saying, this is what you're allowed, this is what I got back, or this is what you see actually, is what it's going to tell it. So there's this hard division here, and basically an interface between the user process and your hardware. Bless you. Any questions about that? All right. All right, process management. We're going to get a lot into this, but keep in mind, as I said earlier, you have a lot of different processes running. You have to figure out how are we going to manage them? How are we going to at least give the illusion that they're all running simultaneously? So we need to allocate the CPU in a fair way, memory in a fair way, I/O in a fair way, or at least in a way that's going to give the illusion of multitasking. Initializing data, when your program begins, it's got to set up your whole program. If you ever run a simulator of an operating system, even just a simple system call one, usually about millions of cycles go by before your program even starts. And that's just the kernel loading everything up, getting everything ready for your program to begin. Because there's a lot of initialization. It's got to allocate the memory, It has to set up all your environment variables. It's got to read your entire program into memory. It's got to make sure you're inside the job scheduler, but we'll get to that in a minute, later on. It has to initialize a lot of stuff. Single thread has one program counter. Of course, if you have multi-thread, you have multiple counters. Those each need to be set up as well. Right. Yeah, there are the tasks: creating, deleting user and system processes, suspending. You would suspend when it's waiting for something from the keyboard or some type of input. That's suspending, waiting. Process synchronization and communication. If you're running multiple processes and they need to communicate to one another, which does happen. Have we done that yet? Any type of process communication?
What do you mean? Like,
Have we done like memory map or set up a socket so that one thing can talk to another? Have we done pipe? Well, we've probably done piping, where you take the standard out and send it to the standard in of another program.
Piping when we're done.
So you've done piping, which is a very basic version, but it does make at least some sense. Well, I mean, that's communication in a way, it's synchronization, right? Because if the second program, if you have this process here and sending it over to this guy, B is waiting for A to write something, right? So the OS is taking care of the synchronization where A doesn't do anything, I mean B doesn't do anything until A has at least given it enough information to continue on. So that's the very basic version of synchronization. So we'll probably go into at least some examples of piping and memory map as well. Ooh, hopefully memory map will work under Bash under Windows. We'll find out. And then deadlock. What if you're in this model and then all of a sudden A, I guess, dies, what happens over here? Well, what should happen over here? So let's put this one should stop, or at least to say, hey, look, that's all you get. But the operating system has to handle that. It can't. It's not like the OS just it magically happens. The OS has to take care of it. It's a lot of things the OS has to do. All right, memory management. All data memory before and after processing, so it's got to manage it, store it out, make sure the instructions are in the right location. Yeah, it's really keeping track of all the different memory. The biggest problem is when you have multiple CPUs. Now you have to figure out, hopefully load the cache. First off, you have to figure out if the cache coherence, aka keeping cache memory, is your job or the hardware's job. You got to figure that out first, and then, or if it's some hybrid, and you got to figure out what you need to do on the software side to make it work. And then, if it is, which process should you put in there? Because, maybe if you have a multi-core system, that was an interesting box. We'll call it an L1 cache, and then over here, you have another L1 cache. And program 2, we'll say, well, programs 1 and 2 are over here. And programs 3 and 4 over here. You ran those two. You probably don't want to swap them, because you've probably been having something in the cache that you could reuse, because they've been using these caches as they swap in and out. So you probably want to keep 3 and 4 running on this guy, and 1 and 2 running on that guy as well. So you need to keep track of that. Again, it doesn't just magically happen. The OS has to take care of it. And this actually becomes problematic, because what if some of these die and then all of a sudden new ones come in, maybe you need to migrate something over. There's a lot of situations that can arise to try and make this optimal. But again, we'll talk about that. All right. When you're writing a program, the main thing here is that you just assume you have memory. You ask for memory, you get memory, and then you just work with it from there. You don't care about what's happening behind the back or with the details of it. That's what the operating system's job is: figure out what that memory actually is, where it's actually located. Oh no, it's on a file. Okay, I need to stop, go and access and load that into memory for you. So the OS, just doing standard memory reads and write, is providing a lot of services for you, while you, the blissful, ignorant application programmer, don't have to worry about, which is a good thing. But do keep in mind that someone has to program this and make it work. File system management, and it's the same thing with files. There's a lot of information with files. How they're stored, how directories are stored, how file systems are laid out. Mass, any of y'all have used SANS? Not SANS, I'm sorry, network attached storage. I did that backwards. Yeah. Whatever, backwards. Dyslexia. Yeah, there's a mass storage management. How do you utilize that as well? Because some operating systems will actually be a cluster. It's one OS that's running on 20 machines. So they're actually trying to communicate, and maybe they have a network attached storage that they're trying to manage as well. Another model, again, you have to take care of all these different storage requirements, namely tertiary storage. Oh, that might be optical, but could also be a network attached storage as well. Okay. Hopefully this was clear in architecture. If not, we'll do it again. Registers, it's on your CPU. Less than a nanosecond to access it. Cache, usually the first piece of memory. Usually it's at least a couple nanoseconds. I've seen it as high as 25. That's about accurate. So it's definitely slower, factory slower, but it's not as slow as main memory. I've actually seen that number go up to 1,000 before. But this is probably fairly, actually this is a little on the low end for nowadays. Memory's still a little slow. I would say the average is probably 300 or 400 cycles. And that's a mistype. That dot should be a comma. Notice the 3 zeros afterwards. So if you have to go to disk, it's really, really slow. The point here is avoid going to disk at all costs. But the flip side is the disk has all the storage that you need. So you got to balance that as well. Managed registers, your compiler takes care of that. Cache in general is the hardware, and that's actually a safe assumption. Operating system takes care of main memory and disk storage. All right. The point here is, what's the life cycle of a process? You load your process up. Well, you got to load it from your disk. It's got to load into main memory, loads into your cache. Then they can start working on your registers. So that's the way it's done. Just keep that in mind, that that's the flow. Hopefully that's somewhat intuitive, but that's how it does flow through your system. Let's see. If you're in a distributed environment, there's maybe a lot more points going on here. Maybe you need to go over the network at some point as well. All right. Because I/O was so complicated, they started coming up with what's called subsystems, which is really an I/O system to take care of a bunch of different I/O devices. A very common one is USB. USB is a very common I/O subsystem. It's basically a framework for how you can attach your different I/O devices. They adhere to the USB protocols, and basically the operating system comes up with its subsystem of how to handle USB. So the point is once you have a USB device, it adheres to a bunch of things, a bunch of protocols. Your device driver that you have to write for your device only has to do a certain couple of things, or far less than if it was a straight serial device. General device driver interface. Best way to think of it. Okay, protection, security. We've already talked about user and kernel mode for protection. But the operating system is going to provide something on top of it. Usually you have something called your user ID for each user. You're going to have your group ID for what group or role that your user is in. And then you have root. Well, in Linux you have root. Windows it's administrator, which has all the privileges. How many of y'all have heard of privilege escalation? Yeah, so we got a good number here. If your user at some point, well, you do have to do escalation at some point, because when you're going from user application to a system call, that is a privilege escalation. But that's a legitimate good one because you're adhering to certain interfaces. Security-wise, your hacker wants to do privilege escalation, or I prefer to call it escalation of privileges. beyond what it's meant to do. And that's another problem that can come up. All right. All right, we do, historically speaking, we've been calling computers many different things. We still want to stick to that somewhat, but do keep in mind that today it's been blurring over time. Because beforehand you used to have your terminal connected to a mainframe. And your terminal, aka what would be our laptop right now, really couldn't do much. It will only interact with the mainframe. Obviously it's a little different now. You have your own PCs, which are kind of like a light mainframe, so to speak, but they run on your machines. And now for this class and a lot of things, it can do all the work you need it to do. Home networks, yeah, so Office, you have a lot of PCs, usually with Portal Home. Single systems and those. Now firewall to network. Yeah, back then firewalls used to be very expensive. Now you can just, it comes default now, really, on pretty much every router you buy. Yeah, computing environment, this is client server. Multiple clients connect some way via network. This picture is of a bus. It doesn't have to be a network bus. It could be something else, although Ethernet is technically a bus. And then they communicate to the server, and then it comes back out. Hopefully this is nothing new. Peer-to-peer, different than, whoa. This is client-server. Peer-to-peer, there are no clients on server. Everyone's a client on the server. So it's literally just distributing out all the information. You join the peer-to-peer network, you register yourself, and now you can start sharing as much as you want. Tell how old these slides are because you've got Napster and Nutella out there, but BitTorrent's still pretty popular. I saw that, I was like, wow, haven't seen Napster in a while. And of course, web, pretty ubiquitous. All of our PCs and even our phones are on it. Another term you want to know, load balancer. How do you come up with the, operating system or architecture on the back end? You want to balance the load coming in. So you need to have, all the operating systems need to be able to report, hey, what's my CPU load? Am I pegged at 100%? Or am I around 30%? I can take a little more work and get some more stuff done. And that needs to be reported back to a load balancer that sees the traffic coming in, what type of traffic it is. All right, go over here. And there's also been a lot of evolution of operating systems. Yeah, Windows 95, wow. Client side, of course, Linux and Windows 10, they'll have a lot of client and server capabilities built in. Naturally, there's a big open source operating systems. Hopefully you've seen that nowadays. Windows, still closed source. Is Mac still closed source? They were open at one point. Are they kind of hybrid now?
The underlying is open source.
The underlying still
They
open?
don't do anything with it anymore.
Yeah, that's what I thought. Yeah, they pretty much closed it up. But open source, everything's open, counter to all copyrights. They usually call it copy left to play on word with copyright. Free Software Foundation has been heading up a lot, and they've been promoting the GNU public license, which is what Linux is under, and actually a lot of other open source tools. GNU, BSD is not under the GNU license, but it's still an open source operating system. Core of Mac OS, that's what we're talking about, is actually open source. Wow, these slides are real old. Oracle Solaris is as well. All right. Okay. We ran through a lot of material. That's just to give you a high-level view of what's going on, generally what we're going to be talking about. Hopefully you can tell that an operating system is very complex. There's a lot of different things moving around and going on. And we need to somehow come together and figure out how we're going to piece them together. Any questions on this before I go to the homework? Nope. All right.
So pretty much all the terms that we guys would be able to test would be blue already, right?
Yes.
We made sure that we knew those were the terms that we
Yes, and as a courtesy on your homework, I list all the terms out because there's a lot of terms.
Yeah, it was